Good morning, students. Let us further proceed about code optimization. As I told you, code optimization is a transformation by which compiler can improve your target code. So code optimization is of two types: machine dependent and machine independent. So we have already discussed what about machine independent and machine dependent optimization. So machine independent optimization, compiler takes an intermediate code and transform a part of code that does not involve any CPU register consideration or absolute memory location. That is independent of machine. So this machine independent is again are of two type: function preserving and loop optimization. So why this is called as machine independent optimization? Let us take an example code having a do while loop. Do, this is the first statement, item equals to 10 is assigned, value equals to value plus item, while value is less than 100. So if you see this particular code, so the assignment operator item equals to 10, this is you can say value 10 is assigned to item in each and every iteration, which is not required. So what optimizer will do, it will you can say move this particular assignment to outside of the loop. So item equals to 10 is initialized from the outside of the loop, and loop will be do value equals to value plus item while value is less than 100. So it should not only save the CPU cycle, but can also be used on any processor. So that is why this kind of optimization is machine independent optimization. Now what is machine dependent optimization? Machine dependent optimization is done after the target code has been generated and when the code is transformed according to the target machine architecture. So it involves basically CPU registers type may have absolute memory references rather than relative references. Machine dependent optimizer put efforts to take maximum advantage of memory hierarchy. So let us discuss what is machine independent optimization. As I told you, this is of two types: function preserving and loop optimization. So what is function preserving? Under this category, we have compile time evaluation, we have common sub expression elimination, dead code elimination, code movement, strength reduction, and this compile time evaluation is further divided into two part: constant folding and constant propagation. So let us discuss these code optimization techniques one by one. So what is constant folding? So in constant folding, as the name suggests, it involves folding the constants. What do you mean by constant folding? Suppose this instruction is given by a programmer. Circumference of circle is calculated as 22 by 7 multiplied by diameter. So this technique evaluates the expression 22 divided by 7 at compile time, and the result of this division 22 divided by 7, that is 3.4, is replaced in the expression at compile time. So this particular constant folding saves time at runtime because the division is a, you can say, costly operation. So the expression is replaced with the respective value in constant folding. Constant propagation. So in this technique, if some variable has been assigned some constant value, then it replaces the variable with its constant value in the further program during compilation. The condition is that the value of the variable must not get altered in between. So if value of the constant doesn't change during the course of execution, so its value will be replaced. Suppose you have this constant defined, pi equals to 3.4, radius equals to 10, and later on in your program, this pi and radius value constants are used. So in this technique, the optimizer substitute the value of variable pi and radius at compile time. So the expression written by you will be converted as 3.14 multiplied by 10 multiplied by 10, and the expression is then replaced with its result, that is 314. This saves the time at runtime. Second technique in function preserving is known as common sub-expression elimination. This expression, the common sub-expression elimination means the expression that has been already computed before and appears again in your code is called as uh, common sub-expression. In this technique, as the name implied, it involves eliminating the common sub-expressions. So the redundant expressions are eliminated to avoid their recomputation, and the already computed result is used in further program when required. Suppose you have a code having statements. So in this code, if you see 4 asterisk I is an expression whose value is assigned to S1, and later on again 4 asterisk I expression is evaluated and it is assigned to the temporary variable S4. So this 4 asterisk I is a, you can say, common sub expression, and here at this point this expression need not to be calculated. So before optimization, this is the code, and when optimizer optimize the code, so the code becomes, first statement is there, second statement remains as it is, third statement remains as it is, but this S4 will be removed by the optimizer. Fifth instruction S5 equals to n remains there, and wherever the reference of S4 is there before optimization, instead of S4, what optimizer will do, it will give the reference of S1, because S1 and S4 are the same value. Next is code movement. Next technique is code movement. As the name suggests, it involves movement of the code. So slight movement of the code may be there. So why this movement is there and what will happen after code movement? The code present inside a loop is moved out if it doesn't matter whether it is present inside and outside. Such a code unnecessarily get executed again and again with each iteration of the loop, and this leads to the wastage of time at runtime. So suppose a loop is for loop is there. Inside for loop, two statements are there. X is equals to y plus z, and a of z is equals to 6 multiplied by j. But if you see this particular instruction, x equals to y plus z. So this instruction, the value of x is calculated again and again, and which is independent of this loop, because in this loop neither y is changed nor z is changed. So value of x is calculated again and again, but it is unchanged. So what compiler, what optimizer will do, it will replace it will move this particular code, line of code, to the outside of the loop. So that is why after optimization, x equals to y plus z is placed outside of the loop, and rest of the loop remain as it is. This approach is called as code movement. Dead code elimination, as the name implies, so it involves eliminating of dead code. So if you see this particular example here, I is initialized as 0, and in the condition expression you are checking its value with 1, I equals to 1, and this I equals to 1 will never happen, because you have just initialized I equals to 0. So this is a dead code, and this code will not be executed at all. So what optimizer will do, it will remove this particular code, and the code after optimization will look like this, I equals to 0. Next technique is strength reduction. So what is a strength reduction? It involves reducing the strength of the expression. So this technique replaces the expensive and costly operator with the simple and the cheaper one. So certain you can say costs is associated with each and every operator. So some operators are you can say cheaper, and whereas the rest of the operators are costly one. So if you take the example, suppose a statement is written in your code b equals to a multiplied by 2, and we know the multiplication operator is a very costly operation. So instead of writing this particular statement in your code, what optimizer may do after optimization, it may replace this instruction b equals to a plus 2 by b equals to a plus a, because plus operator is cheaper operator as compared to multiplication. Now next you can say type of independent optimization is loop optimization. So loop optimization is a technique in which code optimization is performed on inner loops. Various techniques are available in loop optimization. One is code motion, second is strength reduction, third is loop unrolling, fourth is loop fusion. We have already discussed code motion and strength reduction. Now, third one, loop unrolling. What is loop unrolling? In this method, number of jumps and tests can be reduced by writing the code two times. So, suppose uh, you are having a code in which a loop is iterated 100 times, and in this you are executing these two statements: ai is equals to b of I, and I gets incremented each time. So how this code can be optimized? So what compiler may do? Compiler may replicate these two instructions inside the while loop, and the code will remain as it is. So in this particular case, uh, the total number of iteration will be, here in first case total number of iteration will be 100, whereas in this particular case total number of iteration will be reduced to 50. So 50 iteration will be there. So this is how optimizer is optimizing the code. Next is loop fusion. What is loop fusion? Basically, in loop fusion method, several loops are merged to one loop. Suppose a code is given to you. This is the code before optimization. Inside this code, uh, inner loop is there for I equals to 1 to n, for j equals to 1 to m, do a of I j equals to 10. So this code can be optimized by merging both the loop outer loop and inner loop. So we are merging two loops, and your code will look like this: for I equals to 1, j equals to 1, to n cross m, do a of I equals to 10. So this is the, you can say, various techniques of independent code optimization, machine independent optimization. And this is all for today. Thank you.